Okay, now we will do some exercise questions. So the first question is about finding the dimensions. So we need to find the dimensions of linear momentum, frequency and the pressure. So let's start with the first question. So how to find the dimensions of linear momentum? So linear momentum is represented by small p. And the formula of linear momentum is mass into velocity. So it's quite simple. What are the dimensions of mass? It is m, L0 and T is 0. Only mass is there in mass. Then velocity. Velocity has dimensions of meter per second, that is length and time. So we will have m will be 0, there will not be any mass dimension, then L, and T minus 1 because this is 1 over T. Okay, so ultimately the dimensions of momentum will be m, L, T minus 1. Now what about the second one, frequency? So what is the formula for frequency? So frequency is the inverse of the time period. So this is quite simple. Mass m is 0, L is also 0 and T is minus 1 because this is 1 by T. So the dimension of frequency is m0, L0, T minus 1. Now what about pressure? So the formula for pressure, this is capital P, this is small t. So the formula for pressure is force upon area. Now the formula for force is m into a upon area, mass into acceleration upon area. So the dimension of mass is m, dimension of acceleration is meter per second square, that is length t minus 2 upon area. Area is length square. So if you solve this, what you will get, the dimension of pressure will be m, L minus 1, T minus 2. So this will be the dimension of pressure. Now in this second question again we have to find some dimensions, but here the dimensions are of angular quantities, angular speed, angular acceleration, angular force, that is torque, angular inertia, that is moment of inertia. So second question. So in the second question, let's first find the angular momentum of the dimension of angular speed. So the angular speed or angular velocity is usually represented by omega, and the formula for angular velocity or angular speed is angular displacement upon time, that is theta upon time. So there is no dimension for theta. Okay, angle is dimensionless, and the dimension for t is obviously, time is obviously t. So this will be m0, L0, T0, and this will be m0, L0 and T to the power 1. So ultimately the dimensions of angular speed will be m0, L0, T minus 1 because this T will go upstairs. So T minus 1. Now what about angular acceleration? Angular acceleration is represented by alpha, and it is angular velocity or angular speed upon time period. So just now we find out that the dimension for angular speed is m0, L0 and T minus 1, and the dimension for time is obviously t. So it will give us m0, L0, T minus 2. So these are the dimensions of angular acceleration. Now the dimension for torque. Torque is the angular force. Torque, it is represented by tau. Now torque is force into displacement, perpendicular distance. So again the dimension for force, we know that it is m, L, T minus 2, and the dimension for displacement or distance is L. So ultimately the dimension of torque will be ml square t minus 2. So this is torque. Now what about the dimensions of moment of inertia? Moment of inertia is the kind of angular inertia. It opposes the change in the rotational motion. So moment of inertia is represented by I, and it is equal to mr square, mass into perpendicular distance square. So again the dimension for mass is obviously let's write it small m so that you do not get confused, mr square. So dimension for mass is m and dimension for r square will be l square. So the dimension for moment of inertia is m l square t to the power 0. So this is our second question's solution. Now in the third question again we have to find some more dimensions. Now here electric field, magnetic field, permeability etc. are given, and relevant formulas are also given to us so that we can use these formulas to find the values of find the dimensions of various quantities. So answer 3, solution of question number 3. So here what do we have? First of all we need to find the dimension of electric field, which is represented by E. Now electric field is equal to force upon charge. Now again the dimension of force is ml t minus 2 and dimension for charge. Now here we have to use some more formulas or some more dimensions. So here current will be used as the fundamental dimension, fundamental quantity. So charge is equal to current into time period. So that is for current we can use I as the dimension, and for time again we will use t. So the dimension of electric field will be m l t minus 3 I minus 1. Remember this I is another fundamental quantity which is the current. So when we are talking about electricity or magnetism, current will be used as the fundamental quantity apart from mass, length and time. So second, magnetic field was asked. So the formula for magnetic field is force upon qv. So here velocity is extra. So same ml t minus 2 I t, for velocity it is l t minus 1. So after solving this, the dimension for magnetic field will come out to be m l t minus 2 I minus 1. This should be t minus 2, sorry, m t minus 2 I minus 1. So this will be the dimension for magnetic field intensity. Now the third is magnetic permeability, which is represented by mu naught. So this permeability tells us about how easily the magnetic field can travel in any medium. So the formula is magnetic field into 2 pi a. Now a is the length and upon I is the current. So what we will have for magnetic field, we will have m t minus 2 I minus 1. For 2 and pi there is no dimension, and for a, that is length, so it will be L upon current is obviously I. So after solving this you will get m L t minus 2 I minus 2. So this will be the dimension for the magnetic permeability, magnetic field, and this is electric field. So this is how you can do you can find the dimensions. Now in the next question we need to find the dimensions of dipole moment, electric and magnetic dipole moments. So the formulas are given here. So let's try to find the dimensions. So solution for question number 4. So first the electric dipole moment. So it is represented by small p. Just please do not get confused with small p. It is also used for momentum, linear momentum, and it is also used for the electric dipole moment. So please do not get confused. So p into q into l, where q is the charge and l is the length. between the two charges, positive and negative charges. So here again the dimension of charge is current into time, and for length it will be only L. So this is quite straightforward, this is quite simple. So the dimension is L T I, M is 0 here. You will notice that in most of the cases where we have electric or magnetic formulas, different formulas, mass will usually not be there in many of the cases. Now the next is magnetic dipole moment, which is M is equal to IA, where I is the current and A is the area. So what we will have, so we will have for I, we will have obviously I, and for area we will have L square. So ultimately the dimension will be L square I. So this will be dimension for magnetic dipole moment. In question number 5 again the dimensions are asked for the but here something different is there. Here we are asked that what are the dimensions of Planck's constant h from this equation, E equal to h nu. So here what is different is that h is a constant term. Okay, so sometimes people get confused that constant terms do not have dimensions. So it is not necessary. Okay, sometimes constants do not have any dimension, but sometimes they do have dimensions. So remember that it is not necessary that if we have a constant then it will be dimensionless. So here we are asked to find the dimensions of Planck's constant h by the formula E equal to h nu. So this is question number 5. So in this question the equation is E equals h nu. So h is E upon nu. So when nu is the frequency, so the dimension for energy is m L T minus ml2 t minus 2, and dimension for frequency is t minus 1 as discussed earlier. So ultimately what we will get ml square t minus 1. So this will be the dimension for the Planck's constant. Now the turn is for the thermodynamic quantities like specific heat, gas constant, coefficient of linear expansion, etc. So these are thermodynamic quantities. So let's start with question number 6. So the answer for question 6. So first they have asked us about specific heat capacity. So it is represented by C and the formula is Q upon m del T. So where the Q is the heat and the dimension for heat is similar to that of energy, because heat is the form of energy. So as discussed, energy has the dimension ml square t minus 2. So same dimensions will be used, ml square t minus 2 for heat. Heat is also a form of energy. Now next m is the mass, so it will be m only, and del T is the change in the temperature. Remember, this is not time, this is temperature. So change in temperature, so temperature is, we will have a new unit here. For temperature we will use K. Okay, fundamental quantity, just a representation. Okay, K is for temperature, remember, because temperature is measured in Kelvin. So because we have already used T for time, so if we have temperature which also starts with T, then it will be very confusing. So therefore we need to take some other notation and we choose K. So the dimension for specific heat capacity is L square T minus 2 K minus 1. So this is the dimension for specific heat capacity. Now next is the coefficient of linear expansion. So it is represented by alpha, and the basic formula of alpha is the change in length upon the original length into change in temperature. So change in length is obviously L, length is again obviously L, and change in temperature is K. Change in temperature is K. So ultimately what we will get, K minus 1 will be the dimension for coefficient of linear expansion. This coefficient of linear expansion tells us about the ability of any material to expand or contract. Then C is the gas constant. Gas constant is represented by R, and this can be, the dimension can be found out using the equation PV equal to nRT. So from that equation we have R equal to PV upon NT. So where pressure, P is the pressure, so for pressure we will have M L minus 1 T minus 2, because pressure is force upon area. Then for volume we will have L cube, length cube. Then N is the moles, okay, N is the mole. Mole is again a new constant, dimensional constant, and T is the temperature, that is Kelvin. So this is quite interesting. Here we have one more quantity, mole. So M L square T minus 2 K minus 1 mole minus 1. So the dimensions for gas constant. Now in the 7th question we have to take force, length and time as the fundamental quantity. So instead of mass, length, time, etc., we have to take force, length, time to be the fundamental quantities, and then find the dimension of density, pressure, momentum and energy. So this is quite simple. What they are asking us is to tell us the dimensions in the form of force, length and time. So first what they are asking us is about density. So density is mass upon volume. Now mass is force upon acceleration by F equal to ma, and V is the volume. We know that the dimension for volume will be L cube. So what we will have, we have to keep in mind that we have force as the fundamental quantity here. So F will be F, and for acceleration we will have L T minus 2 L cube. So ultimately what we will get, the dimension will be force L minus 4 T square. So this will be the dimension of density in terms of force, length and time. Similarly we can find for different things, like next is pressure. So pressure is force upon area, so it is quite simple, F upon L square. And now this can be F L minus 2, okay. Then next is the momentum. Linear momentum is mv. So mass is force upon acceleration into velocity. So this velocity is there, then we will get F L minus Lt minus 2 for acceleration. Velocity is Lt minus 1. So ultimately for momentum we will have force into time, Ft, the dimension. Then energy. Let's say energy has one formula, half mv square, and this can be written as force upon acceleration for a mass and velocity square, so which will give us F upon Lt minus 2 L square T minus 2, because we have to take the square of the velocity. So this will give us Fl. So this is the dimension for energy in terms of force and length and time. Now the next question, question number 8. In question number 8 it is given that suppose the acceleration due to gravity at a place is 10 meter per second square. So we need to find its value in centimeter per meter square. That is, we have to convert the units here. So how to convert the units. So this is quite simple. So we know G is given as 10 meter per second square. We need to convert it into centimeter per minute square. So you can write it like this: 1 meter upon 1 second square. At the place of 1 meter you convert it into centimeter, so it will give you 100 centimeter, because 1 meter is 100 centimeter. And what is this can be written as 1 second into 1 second, 1 second into 1 second, because it was a square. So 1 second is equal to how many minute? So 1 by 60 minute. So minute square, 2 minutes are there. So G will be equal to 36 into 10 to the power 5, or you can also write 3.6 into 10 to the power 6 centimeter per minute square. So now let's concentrate on question number 9. It is given that the average speed of snail is 0.02 miles per hour and leopard has speed 70 miles per hour. So we have to convert these units into SI units. So this is again quite simple. SI unit for speed is meter per second. So we have to convert miles per hour into meter per second. Answer 9, solution 9. First, for the snail, the average speed is 0.02 miles per hour. Okay. Now let's convert. So 0.02. Now what is 1 mile? So 1 mile is equal to 1.6 into 10 to the power 3 meters. 1.6 into 10 to the power 3 meters. And what is 1 hour equal to? 1 hour is equal to 3600 second. 3600 second. So what we will get after simplification? We will get approximately 0.0089 meter per second after simplification. Now for the leopard, the speed was 70 miles an hour. So again 70 into 1.6 into 10 to the power 3 upon 3600. So after simplification we will get 31 meter per second. So this will be the velocity of leopard in SI unit. So this is quite simple. Just remember a few conversion factors, that is what is 1 mile equal to, what is 1 meter equal to, what is 1 centimeter equal to, what is 1 second equal to, what is 1 hour equal to. Just remember these few basic things. So now we can move on to answer number or solution number 10. So what is solution 10? So the height of mercury column in a barometer is given and it is recorded to be 75 centimeter. So now we have to calculate the pressure in different units. Okay, so we have to calculate the pressure in different unit. So let's try to do this question number 10. So first of all, height is given 75 centimeter. Density, I am representing density by rho. So density of mercury is 13600 kilogram per meter cube, and the acceleration due to gravity is 9.8 meter per second square. So the pressure has a formula H rho G. Height is given, it is 0.75 meter into 13600 kilogram per meter cube into 9.8. So after solving this you will get 10 into 10 to the power 4 and the unit will be Newton per meter square. And if you need to, this is SI, if you need to find in CGS, that is dyne per centimeter square, then you will get 10 into 10 to the power 5 dyne per centimeter square. So this is question number 10. Now what about question number 11? So we have to express the power of 100 watt bulb in CGS unit. So what is SI unit? We have to convert into CGS unit. So solution for question number 11. So 100 watt is given. So we know that watt means 100 joules per second. So in CGS unit what we need to convert is in erg per second. So 1 joule is equal to 10 to the power 7 erg. So this is quite simple. 100 joule per second is equal to 100 into 10 to the power 7 erg per second. So it will give us 10 to the power 9 erg per second. So this will be the value in CGS unit. In question number 12, it is given that the normal duration of ISC physics practical period, that is the practical period of physics class in Indian colleges, is 100 minutes. So you have to express this in micro centuries. Okay, so this is quite interesting. 1 micro century is 10 to the power minus 6 into 100 years, because century is 100 years, so micro is 10 to the power minus 6, so micro century is 10 to the power minus 6 into 100 years. So the solution for question number 12. So 1 micro century is equal to 10 to the power minus 6 into 100 years. After solving this, we will get 10 to the power minus 4 years. So 10 to the power minus 4 years, we need to convert this into minutes, because we want to find in minutes. So 1 micro century is equal to 10 to the power minus 4 years, and 1 year is equal to 365 days, 24 hours, 60 minutes. So this will give us in minutes. So 100 minutes will be equal to 10 to the power 5 upon 5 to 560 micro century. So after simplification, 100 minute will be equal to 1.9 micro century. So in 100 minutes 1.9 micro centuries will be there. Now we have to convert in question number 13 the units 72 dyne per centimeter into SI unit. So answer 13, 72 dyne per centimeter. So the SI unit is Newton per meter. So 72 into, now what is 1 dyne? It is 10 to the power minus 5 Newton, and 1 centimeter is equal to 10 to the power minus 2 meter. So we will get 72 into 10 to the power minus 3 Newton per meter, which can be written as 0.072 Newton per meter. So this will be the value in SI units. Now let us try to do question number 19, which is a bit different. So let x and a stand for distance. Okay, so x and a has the dimensions of distance. So we have to check whether this two sides are equal, dimensionally equal or not, dimensionally correct or not. So solution 19. So one side is dx, integration of dx upon root a square minus x square, and the second side is L upon root L square minus L square. Obviously this leads to L to the power 0, this part. So let's check what we have for the different part. So this is our LHS, Now what about the RHS? So RHS is 1 by A sine inverse A by x. just again repeating, dimension of length is L, dimension of length is L. So here again what we have is 1 by L, and this is dimensionless. So what we have, L minus 1. So this is dimensionally incorrect. So this equation is incorrect dimensionally, and if something is dimensionally incorrect, that means that it is obviously incorrect. So this equation given is incorrect.